All right, hi everyone. Welcome back to my exam 3 review part 2. This part is going to be all about alkenes, how to name them, what reactions they go through, all of that types of stuff. But let's talk a little bit about the terminology for alkenes as a whole before we really start. So an alkene overall is anything with a carbon-carbon double bond. And we can either have something called terminal alkenes or internal alkenes. A terminal alkene is exactly how it sounds. The double bond is at the very end of our carbon chain. And an internal alkene is when it's not at the end of the carbon chain. And a cycloalkene is when the double bond is part of a cyclo. All these names are pretty self-explanatory. I just want to gloss over them very quickly in case you've heard of them and just nobody's ever explained to you what they are before. In addition, when we're looking at alkenes, each side of the alkene is going to be sp2 hybridized, which means it's going to be trigonal planar. So this whole alkene here, this is sort of laying flat on our, it's laying flat like a piece of paper. So instead of drawing it like we have before, like with this tetrahedral representation, we only draw it with lines because that is a good representation because everything will be on the same plane. And sometimes you might also see alkenes drawn like this. And this is sort of to represent if it's on its side. And that's what this sort of thing is, this diagram here is sort of showing, is an alkene on its side where we have two legs of the alkene pointing back and two of the legs of the alkene pointing front, so both of these are correct demonstrations of an alkene, both of them representing an sp2 trigonal planar atom, or trigonal planar molecule, okay? And so then one more thing we want to talk about is we can see here that whenever we recall back in, like, I don't know what it was, chapter 1, I think, where we talked about structure and bonding, a double bond, so all single bonds are going to be made up of one sigma bond. That's an alpha, that's not a sigma. One sigma bond. That is a single bond. So we can say that one of these bonds is going to be a sigma bond. I'm just going to choose this bottom one right here. Anything extra, so like a double bond or a triple bond, is going to add one or two pi bonds. There's going to be one pi bond for every extra bond. So in this case, we have one sigma bond and one pi bond. If we had a triple bond, then we would have one sigma bond and two pi bonds, and so on. And what's important to note here is that the sigma bond is hard to break, whereas the pi bond is a little bit easier to break. So what that means is we have sort of like what can be considered here an extra pair of electrons in the pi bond, which is what we are going to be talking about as far as reactions goes in this chapter. So let's move on a little bit to degrees of unsaturation. So when we talk about degrees of unsaturation, we have to talk about saturation first. So a saturated hydrocarbon is a carbon with the maximum amount of hydrogens for the number of carbons. So we know that carbons can have 4 bonds, and we know that it has to either have 2 or 3 carbons attached to it. It just depends on how many other carbon-carbon bonds it has. And so the mathematical representation for the maximum number of hydrogens, given a certain number of carbons is 2n plus 2. So for example, in here, if we have 5 carbons, so 5 equals n, which equals carbons, the number of hydrogens that we want is 5 times 2 plus 2, which equals 12, which equals the number of hydrogens in these states, okay? So we can see here that these top 3 representations, these are fully saturated. But we call something unsaturated when we do not have the maximum amount of hydrogens for the number of carbons that we have. So in this case, we see that we have 10 carbons instead of 12. In this case, we see we have 8 carbons instead of 12. So there's sort of a mathematical equation to determine how many degrees of unsaturation that we have for how many carbons we have versus how many hydrogens, how many oxygens, all of these other atoms. And that could be shown right here. Okay, so yeah, it's not written out here. But essentially what you want to do is you want to count the number of carbons. That's going to be our n. And then we want to count the number of hydrogens. I'm going to call that just lowercase h, okay? So what we're going to do is we are going to add H plus however number of halogens that we have. So remember, halogens are Cl, I, Br, all of those. And the reason why we count those the same as hydrogens is because similar to hydrogens, they can only have one single bond. It's just instead of only wanting two electrons, such as in hydrogen's case, these guys already have 7 electrons, so they only want one more bond. And somebody asked, would he give us the structure or just like have it written out, do you think? I think what he would do is he would say, given this molecular formula, so that would be like, I don't know, you could be like C6H10, I don't know, Cl, he could ask you how many degrees of unsaturation are present in this molecule. Okay, actually this would be Cl2. And so I'm going to show you how to determine that number. So what you do is we have the number of hydrogens plus the number of halogens. You ignore oxygens because oxygens are sort of like they either act as a link between two carbons or a link between a carbon and a hydrogen. And we can see here that this wouldn't change the actual degrees of unsaturation because it does still have a hydrogen attached to it, so it doesn't really replace any hydrogens. And then we want to subtract nitrogen. So, subtract nitrogen. And this is because if we look at nitrogen, so like carbon attached to nitrogen, the nitrogen will have 2 additional connections. So we could sort of think of those connections as either 2 hydrogens, 2 other carbons. So they just sort of add to the number of hydrogens. So that's not going to make it. It's going to decrease the degree of unsaturation. So that's why we subtract. Okay. So to find the degree of unsaturation, we have the number of hydrogens plus the number of halogens minus the number of nitrogens. And what we do here is we're going to subtract this whole number from that 2n plus 2 that we talked about before, where C is the number of carbons is n, and then we're going to divide this whole thing by 2. Okay? So let's say, for example, oh, that looks like a Z. Let me do 2. So let's say, for example, we take, I don't know, C5H10. So if we did C5H10, 2n plus 2 for that would be 12. So we're going to do 12 minus, we have 10 hydrogens, 0 halogens, and 0 nitrogens. So that's going to be 12 minus 10 over 2, which equals 12, or not 12, but 2 over 2, which equals 1, which means we have 1 degree of unsaturation. Now, for every degree of unsaturation, we either have 1 pi bond or 1 ring. Okay? So if we scroll up really quickly, we can see in this first case here, we can see that it has a pi bond right here. Another example of C5H10 would be a cyclopentane. Because if we look here, each one of these carbons here has 2 hydrogens. So if we go 2, 4, 6, 8, 10, it only has 10 hydrogens, which shows that that ring represents 1 degree of unsaturation. And then we can see here C5H8, 5n plus 2, since we've done that so many times, it's 12 minus 8 over 2. That's going to be 4 over 2, which equals 2 degrees of unsaturation, which means 2 pi bonds, 1 pi bond, 1 ring, or 2 rings. Okay? And then you'll do that with all of the you'll do that with all the different sort of molecular formulas that are given. So a good question for this would be, let me make up something on the fly really quickly. Let's say that I said we had C8H9O2 Cl, and I was like, okay, so how many rings could we have? How many pi bonds could we have? Or how many of the combination could we have? So what that's really asking is what is the degree of unsaturation for this guy right here? So if we do 2n plus 2 for 8, that's going to be 16 plus 2, that's going to be 18, minus the number of hydrogens. We ignore the oxygen, and we subtract the number of halogens. So now we have 18 minus 10 over 2 This should be over 2. So then we have 8 over 2. We have 4 degrees of unsaturation. So we could have 4 pi bonds. We could have 4 rings. We could have 1 ring, 3 pi bonds, and so on. So there are 4 degrees of unsaturation, with each one of those degrees representing either a ring or a pi bond. Okay? And so when we talk about unsaturated, that means we do not have the maximum amount of bonds. Somebody asked, I thought we add the halogens to the hydrogen and only subtract the nitrogens. Yes, what did I do there? Oh, hold on. Oh, I'm sorry. This should be a plus sign. I just dropped the plus. It's 9 plus 1. I did do the addition. I just put minus instead of plus. Sorry, guys. But this is still the same thing. Okay? Okay. So when we talk about the degree of unsaturation, essentially what that means is if we have the pi bond, we have a place where we can add something. So we can get rid of this pi bond because remember, each one of these carbons on either end of this double bond here only has 3 bonds. So like this would be an H, this would be an H. And remember, a carbon can have a maximum of 4 bonds. So what can happen here is this double bond can get taken away and then be replaced on each of these carbons with something new. Okay? And so then that's what the crux of this chapter is about. It's about the addition reactions to alkenes. But before we get into that, we have to talk about how do we name alkenes, because I think that's the first part of every single chapter. Oh, okay, so this is telling us what is the degree of unsaturation in the following compound. This is sort of what we did before. Let's do this one more example before we get into nomenclature. So 16 times 2 is 32 plus 1, that's 33, minus 13, the oxygens don't count, plus 1 for the 1 halogen, minus 2 for the 2 nitrogens, okay? So we have 33, oh, and this is all over 2. And so then we have 33 minus, I think that's 12 over 2. And that is, hold on, I'm trying to do the math in my head. That would be 21 over 2. Did I do some math wrong? Hold on. This should be even. Oh no. That's kind of weird. 16. Oh, I said yeah, I'm sorry. I did 2n plus 1. That's what I get for not drawing out not writing out my work. God, all of my former math teachers are really mad at me right now. So it'd be 34 minus 12, which is going to be 22. Yeah, sorry about that, guys. So then we have 11 degrees of unsaturation. And then if we look over here at this representation, each one of these rings is 1, 2, 3. So each of those rings altogether, that represents 3 degrees of unsaturation. 11 minus 3 equals 9. Again, not writing out my work, that's 8. So that means we have to have 8 pi bonds. And if we sort of look through here, we have 1, 2, 3, 4, 5, 6, 7, 8. And so that is how the degrees of unsaturation sort of are reflected into a physical or like a drawing of a molecule. So a question I was thinking, where did the 3 come from? Oh, I subtracted 3 because we have 3 rings. And since those are kind of obvious to see, I just sort of subtracted 3 to find how many double bonds we would have to have for this actual molecule to exist. We do take in consideration the Cl. The Cl is this plus 1 right here. However, the oxygen is the one that we sort of ignore. Okay? And so a question that sort of reflective of this example would be something like, given this structure, given like this molecular structure, what degrees of unsaturation does this have? And then all you would do is count up the cyclos, or the circles, the rings, and the double bonds, and then that would tell you we have 8 degrees of unsaturation. Okay? And here's some more examples. Okay, so now we're getting to naming alkenes. So before, when we were talking about carbon-carbon bonds, we were talking about alkanes. Notice the difference in the ending of the name there. And so we can say, remember when we were talking about the sort of the base names for like methyl, ethyl, propyl, all that stuff? So what we can do is we can take the first part of that name. So let's take eth, for example, eth, and ethane would mean we only have single bonds, which means it's an alkane. If we have ethene, then that means it has a double bond somewhere, so it's an alkene. And that's why we changed the end of the name, because we're going from an alkane to an alkene. And we can see here that when looking at the double bond, we can see that pentane versus pentene, and it can also change the parent chain. Because when we're naming an alkene, we want to give the longest chain that includes the double bond to be the parent chain, rather than the longest chain overall. So we can see here in this first example, without any double bonds, the parent chain is octane. And now with nothing else changed except we added a double bond to the shorter carbon chain, that parent chain changed from octane to heptene. Technically, yes, this octane chain here is still the longest continuous carbon chain. However, since it does not include that double bond, we do not consider it our parent chain. Okay? And so we also want to give the double bond the lowest number possible. If you remember in my past exam review, part 1, or if I talked about alcohol naming, we give the OH the higher priority, and that's the same thing here. We give the double bond the highest priority. So what we want to do is we want to give that double bond the lowest number possible, even if we can give other substituents lower numbers. So we can see here that if we use the incorrect naming on the left here, this guy right here, then we would have a methyl on 2, 2 methyls on 3, so 2, 3, 3, and then our alkene on 5. We can see, yes, I see your questions. I'm going to get which one's a higher priority when we talk about alcohol. I just want to talk about this first, just as an example, sort of outside of using an alcohol along with an alkene. And so we can see here that if we use the incorrect naming system, we give our substituents 2, 3, 3, 5. And then when we look at the correct numbering, we give our substituents 6, 5, 5, 3. So overall, the incorrect naming has a lower number overall, but we want to give the double bond the lowest number possible. So even if it seems incorrect as far as the numbering goes, it might be correct because you want to give that double bond the lowest number possible. Okay? And there are 2 ways you can indicate where that double bond is. You're always going to indicate where that double bond is by telling us the number that it starts on. So in this case, it starts on 2. If it were to start on, if we said trimethyl 3 heptene, then that would imply that our double bond is right here, and that would be incorrect. So that's why we always indicate which carbon the double bond starts on rather than where it ends or both of them. Okay? So trimethyl 2-heptene versus trimethyl heptuene. Either one of these is correct. Personally, you'll probably see me using this one more because I feel like personally to me, like when I'm writing out names, I feel like this system is a little bit clearer because it puts the number right next to the ENE, the actual substrate, what is actually being modified in this name. So it sort of stays consistent with this other stuff here, like 5,5,6 trimethyl. Okay? So you'll see me using this bottom one more, but both of them are correct. Okay, so let's talk a little bit about OH, a hydroxy group versus a double bond. So we've already covered that both of these have priority, but which one of these have priority over the other? So let's say that we have this guy right here. And there are 2 ways to name this. We can either go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. We can either put the OH on the lower number, such as with the pink numbering system, or we can put the double bond on the lower number with the orange system. It's a little bit arbitrary sometimes, it may seem, but we are going to put the alcohol on the lower number, thus giving it the higher priority. And the way that I like to remember it is, so we see this is this is going to be pent. So our parent chain is PENT. And then we're going to say this is going to be pentene all. And we can see here that the ENE, which is the alkene part, comes before the OL part. So we can that's how I like to remember. If it comes later in the name, then it's going to be more important. It has a higher priority. So the alcohol group has a higher priority over the alkene group. Okay? Okay. So now let's talk about cycloalkenes. So this tends to confuse people sometimes because even though it may seem like we're trying to give the lowest number possible to all substituents, it doesn't really seem that way, such as with this second example here. But let's talk a little bit more about alkene. Oh, somebody asked, could it be pent 3-ene 2 all in my last drawing? This one right here. And the answer is correct. So it'd be pent 3-ene 2 all, or you could also say 3-pentene 2 all, but that's why I like to keep the numbers in the name physically, because it gets confusing when you have more of these suffixes overall. Okay? Does that make sense? Okay. So I'm going to assume it makes sense, and I'm going to continue on to this next part. So when we are naming rings, we are going to find the double bond no matter where the double bond is. What we are going to do is we're going to give either side of that double bond the designation of 1. Because remember that when we are thinking about priorities, the double bond has a higher priority than all these other groups, so we are going to want to put it on 1. What's also important to note is that the other side of the double bond has to be 2. We can't make so like in this example here, I'm going to clear my drawings and zoom in here. We cannot make this 5 carbon 2 and make this 3 4 5, because then that would be wrong. Because remember, when we're talking about double bonds, when we note where that double bond is, we note the first carbon it's attached to. So if we say it's attached to 2, then it would be attached to 3. Okay, that's in linear structures. In cyclostructures, we always give the double bond the designation of 1. And so to keep our naming system consistent, we have to make whatever other carbon is attached to that double bond 2, which can be a little bit rough when we end up talking about the sort of priorities. So we can see here, in this example right here, we could either name it 1, 2, 3, 4, 5, 6, and pretend you don't see the answer right here, or we could number it 1, 2, 3, 4, 5, 6. So the pink numbering system is more correct than the red numbering system. So for people who might be colorblind, the numbering on the outside is more correct than the numbering on the inside. And this is because, again, we want to give our substituents the lowest number possible while also keeping the double bond on 1 and 2. And so then that's why the name is 4-ethyl 3-methylcyclohexene. And that's also why we end up dropping the 1 from the cyclohexene name or whatever cyclo that you have, and that's because the double bond is always going to be on 1 for all of our intents and purposes. Okay, so now let's talk about something that's a little bit tricky. So whenever you have a substituent on either side of the double bond, so we see this guy right here, let's ignore that this chlorine is here for now. We are always going to give the side of the double bond that contains the substituent the designation of 1. Okay? And this is because in 9 times out of 10, this is going to give that substituent a lower number overall. Okay? So this would be 1, 2, 3, 4, 5, 6. And this seems a little bit counterintuitive because if we started numbering from the left or the right side instead of the left, then we put everything on a lower number overall. But because of these IUPAC rules, we have to make that carbon that has that substituent as 1. Okay? So we can see over here that the same thing occurs where we make the carbon with the substituent 1. 2, 3, 4, 5, 6, even though there may technically be a better way, or a quote unquote better way to name this in a way that gives the substituents the lower number possible. This is just the rules that the IUPAC has come up with, just to make sure that everybody has a consistent way of naming things, okay? And this confused me when I was taking Orgo 1. So just keep it in the back of your mind if you're ever asked to name a cycloalkene. Okay? So here are some more examples here. Let's do this bottom right one here, because you can see here we have 2 double bonds. And so what do we do then? So what we want to do is we are going to compare these 2 double bonds. So this one here and this one here, and we are going to use the same rules as before. We're going to want to put one of these double bonds on one and one of these double bonds on and then, okay, let me say that again. I'm sorry, I don't know what my words are doing right now, but we're going to make one of these double bonds as one. So it could be any one of these ends. So like 1, 1, 1, 1. But the way that we determine which one is going to be 1 is we look at which one's the most substituted. In this case, it would be this guy right here. So we go 1, 2, 3, 4, 5, 6. Okay? And so we see here that we have a double bond on 1 and 2, and then 4 and 5. So since we have 2 double bonds here, instead of having ene as our suffix, we're going to have ene. Sorry. It's going to be the same sort of idea as when we talked about when we have 2 OH groups. It's going to be diol. In this case, it's going to be diene. Okay? So let us draw this out really quickly. So I'm going to ignore that both of those methyl groups really quickly and just focus on the parent chain. So we know the parent chain is going to be cyclo, hex, blank, diene. And in this case, personally, I would put 1, 4. Because we have diene in the name, that tells us we have 2 alkene groups, 2 double bonds. So I like to always designate where my double bonds, or where my functional groups are, if I have 1 or more, or if I'm indicating where 1 or more are. And that's why I'm not dropping the 1 in this case, and instead putting 1, 4. Somebody said, why wouldn't it be 1, 3? If we count this, we have 1, 2, 3. The double bond isn't on 3. And yes, and counting to the left again. So somebody said, what if we took this guy and we said this was 1 and went 2, 3, 4, 5, 6. And this numbering system would be incorrect, just because, remember, we always want to put that double bond on adjacent carbons. So we want to put that double bond on 1 and 2 instead of 6 and 1. Okay, does that answer your question? Okay, perfect. And so back to this thing. So we say it's cyclo hex 1,4-diene. And so now what we're going to do is we're going to put in these methyl groups. So we have a methyl group on 1 and a methyl group on 6. So we're going to say 1,6-dimethyl. And then all we're going to do is combine those 2 parts of the name together and end up with 1,6-dimethyl cyclo hex 1,4-diene. Okay, this one's pretty difficult. I don't know if he would ask you that on the test. I would be ready for it if it's on the PowerPoint, then technically it's fair game. Okay, this is a hard one though. Is it supposed to be cyclohexa or cyclohex? So remember when we were talking about a little bit earlier, when we say alkane, so in this case, a cycloalkane would be named like this. So that would mean that our cycloalkane is made up of only single bonds. When I say cycloalkene, and this ALK can sort of be any number here. So that alk could be hex, it could be meth, it could be whatever. So like if I said it was hex, then it'd be cyclohexane, whereas a cycloalkene ends with ene. So it'd be cyclohexene. Okay? So that's why we don't put hexa, instead we just put ene. And that's the main difference between when we talked about like if we had instead of having two double bonds, we had two OH groups. This would be cyclohexane diol. But in this case, we drop that whole A and E part because instead of being an alkene, or instead of being an alkane rather, it's an alkene. Okay. So there would still be a dash between the 1,6 and the dimethyl though, right? Hold on. Oh yeah, sorry, I dropped that. I probably drew it, but my pen didn't pick it up. But yes, there's a dash between 1 and 6, and then dimethyl-cyclohex, 1,4-diene. Okay, so now let's move on. So again, here are some common names. These are not the names you're going to put on a test if he asks you for the IUPAC name, because these are common names and not actual official names. And one more thing that we have to talk about is cis-trans versus EZ. So this entire chapters beforehand, we've been talking about cis versus trans. And when we use the wording cis versus trans, at least with alkenes, we are specifically talking about the same type of compound. So we see here, we have two methyl groups. They're on the same side, so they're cis. Trans, we have two methyl groups. They're on opposite sides, so they're trans. Okay? However, if we get into other examples like right here, we cannot call these cis or trans. Instead, we are going to use something called E and Z. And the way that we do E and Z is we sort of think of it as slicing this molecule in half down the middle and separating these two like parts that have bisected into two separate sort of categories. So we'll call this left and we'll call this right. I hope you can see my R. And so what we're going to do is we are going to assign priority high or low to each atom on each side. So let's look at the left side first. And we're using the same priority rules as we did with the stereochemistry chiral centers. So we can see here that the Br is has a higher atomic number than H. So it's going to be our high priority, and H therefore is going to be our low priority. Okay, instead of using 1, 2, 3, 4 with the priorities, we're just doing high or low. And now if we do the right side, we do the same thing. Cl has a higher atomic number than carbon, so it's going to be high and low. And we can see when the highs are on the same side and the lows are on the same side, we're going to call it Z for Z-zame Zide. It stands for a name, but I don't remember what it is. The only thing that I ever remember is Z Zameside, and that's what Z is for, at least in this case. Okay? So now what about the other example here? So we can see here that bromine is still high, H is still low, and the same thing is still over here. Cl is still Cl is still high, and CH3 is still low. However, we see here that H and L are on opposite sides. So we call this opposite. So it's going to be the E configuration. There's not really good mnemonic for E. Just know that it's the opposite of Z. So it's the opposite. So you have Z and E. Z is for when we're on the Z-zame side. E is when we're on the opposite sides. Okay? So I think there's an example over here. Okay. What if somebody asked, what if the Cl was on the red side? Then that would throw everything off. So somebody's asking, what if instead of on the blue side, on the right side over here, the Cl was on the red side? So let's say that instead of H, or instead of instead of H, we have Cl. And the same thing, we have CH3, and then, I don't know, Cl, same over here. So now what we have here is if we separate each side, we're still going to do the priorities for each of one of these. Bromine has a higher atomic number than Cl, so it's going to be the high, and Cl will be the low. On the right side, it's still completely separate from the left side, so the Cl is still going to be high, CH3 is going to be low. And so we can see that this guy here is considered to be E. Now, something important to note is that at the same time, this guy would be considered to be cis, because we can see here that the Cls, which are the same exact group, are on the same side. So we consider this cis but E. That's why I always prefer the E versus Z configuration, because it seems it's a bit easier it's easier to keep straight, versus cis or trans, okay? And somebody said, why aren't we splitting it horizontally? So, hold on, let me erase some stuff here. So if we split it horizontally, let me go back into drawing, CL. So what if, and somebody said, what if we split it horizontally like this? We can't really do it that way because when we're doing E or Z, we're comparing the carbons that are right here on either side of the double bond, and we can't exactly split that in half. The only time that we would split it horizontally is if our double bond was vertical like this. Okay? So like Cl, Br, Cl, CH3, whatever we did here. So like these two things are the same thing, except one is drawn horizontal and one is drawn vertical. So we split the vertical one horizontally. We split the horizontal one vertically. Okay. So somebody said we only use E or Z when we have 4 different groups. We only use cis or trans when we have the same group. So E or Z can be used for anything. That's why I prefer it. Cis or trans can only be used when we have the same group. So that is why I personally prefer E or Z over cis or trans, because E and Z can be used over a larger swath of stuff. So like we can see here, like technically, yes, this guy is cis, but I'm personally gonna call it E rather than cis or trans. Okay. Uh, and then hold on. So somebody else asked, what if instead this chlorine right here was a hydrogen? Okay. So let me just erase all this stuff here. So what we would do here is, so like now this guy's hydrogen. So now the CH3 is high and the H is low. The Br is high still and the Cl is low. So this guy is just Z. And it's not cis and it's not trans because we don't have two of the same group to compare. Okay, and just to clarify, the same group has to be on either side of the double bond. They can't be on the same side of the double bond. So we can't have like 2 Cl's on this side and say, oh, but we have the same group, so we can use cis or trans. No, we have to have a Cl on one side and then a Cl on the other side. So we have to have 2 of the same group, one on either side of the double bond to do cis or trans. Okay. So in order to add this to like a name, okay, so it's not here, but in order to add this to a name, so let's scroll up a little bit back to the examples that we had a little bit earlier. If it'll load. Yeah, so right here. So I'm going to use this example here. The name's already written out for us. So we would use one of these names just the same, but then we would just put parentheses E or Z in front of it. In this case, we can see that there are invisible hydrogens here. Here's our high group, here's our low group. Here's our high group, here's our low group. The highs are on opposite sides, the lows are on the opposite sides. So this would be E-556 trimethylheptuene or E, E-556 trimethyl-2-heptene. Either one of these would be correct. Just the important thing to take away here is that, like with stereogenic centers, you're going to put E or Z first, and before you ask, you don't really see stereogenic centers and E or Z in the same question. That is not very common at all. Okay? Okay. We always write out E or Z when there's a double bond. Yes, as long as there are different groups on either side. So like if for example, like I'm going to scroll down here, I had a double bond where it looked like this. I can't really assign high or low to either of these because they're exactly the same. So if they're exactly the same, then we don't do E or Z. Okay? So if these are H's, if they're CH3s, if they're Cl's, if they're the same thing on the same side, then we can't really say E or Z, cis or trans. Okay? So do we have to label which carbon the E or Z is at? The answer is no, because it's implied here. Oh, if we have more than one double bond, yes. But for one single double bond, then no. So like if I had 1, 2 ene, then I would have to designate 1 E, 2 Z, that sort of thing, yes. But if we only have this single double bond, then no, you don't label which one it's on. Okay? Okay. So now let's talk about addition reactions. So I'm sort of going to, I'm going to switch my screens here really quickly, and I'm going to switch over to my personal sort of document here. And I have a few more documents that I have added to the exam 3 folder on Google Docs. The Google Docs link is going to be both in the description of this video and the last video if you already have it. And these documents, the alcohol reactions, epoxide reactions, and ether reactions will be included. But what I'm going to focus on right now is this chapter 10 reactions, which will also be included. Okay? So there are 5 different reactions for addition reactions as far as alkene goes. There's hydrohalogenation, hydration using an acid catalyst, halogenation, halohydrin formation, hydroboration oxidation, and this seems really overwhelming when it's all like thrown at you at once, but once you break it down, it'll be a lot easier. So let's first look at hydrohalogenation. So we can see here that each one of these names that is associated with these additions, they have meanings. They're not just named that for no reason. We call hydrohalogenation that because of hydro, we're adding a hydrogen. Halogenation, we're adding a halogen. Okay? And so we can see here that in the first step of hydrohalogenation, we have this HX, where X is like Cl, Br, I. So if we have like HBr, that X is Br. Okay, so then we can see here that recall when we said before we have a pi bond that's easily broken. A pi bond is basically 2 electrons in a pair. So what can happen is it can go ahead and grab this hydrogen right here off of that HX. The HX bond will break and the hydrogen is added to the carbon or the alkene, which then becomes a carbocation. And notice here that when we make the carbocation, again, we want to make the most stable carbocation possible. So what happens is the hydrogen is added to the less substituted carbon. Because again, we want to make a more stable carbocation, and the more stable that carbocation is, the the more substituents that carbocation has, the more stable it is. So in this case, we have a secondary carbon versus a tertiary carbon. So the hydrogen adds to that second, oops, that is not a 2. So that hydrogen adds to that secondary carbon, and the carbocation, the positive charge, ends up on the tertiary carbon. And you may be wondering, where did this positive charge come from? Well, remember when we say that when a carbon has a formal charge of 0, that means it has 4 bonds. And in this case, in this carbon right here, those 4 bonds are this bond right here, and then this double bond makes up 2 bonds. When that double bond goes away in order to make this hydrogen bond, it the carbon becomes a 3 bonded carbon with no lone pairs and thus becomes a carbocation. Okay? In addition, recall when we talked about SN1 and E1, a carbocation is sp2 hybridized, which means it's going to be trigonal planar. So that means that the halogen, which is the X, can attack either from the front or from the back, which means we can get syn or anti-addition. And basically what this means is syn means they're both added on the same type of wedge. So they can be both added on solid wedges, both added on dashed wedges, or they can be added anti, which means they will be added on opposite wedges. One will be on a solid wedge, one will be on a dashed wedge. Okay? Does that make sense to everybody? And that overall is going to be hydrohalogenation. So here's the mechanism for it. And you can see for the reagents, we have to have an alkene plus an H and an X. Somebody asked, are there always going to be 2 wedges and then the wedge and the dash? Yes, so when we're talking about the stereochemistry of an sp3 carbon, recall that for an sp3 carbon, it has to have 2 lines, 1 dashed wedge, 1 solid wedge. And most of the time, you're going to write the products as either a dashed wedge or a solid wedge, which is why I write them as that in this case here. And they said, are there always going to be 2 wedges and then are the products always going to be wedges? Like are the reactants always going to be added as wedges? Not always. So, an example, but the reason why I did it as wedges here is because I find it a little bit more clear than the syn or anti addition when using just lines. If we were just using lines, then the syn addition would look like our reactant, and our reactants are added here. So our H is here, our X is here, and then anti would look like this. I just feel like it's more clear overall if we show it with wedges rather than just regular lines. So that's why I personally write it with wedges rather than lines. And for the products, we do get the syn and the anti products. Okay? And somebody said, is syn caused when it is a front side attack and anti when it's backside? Yes, exactly. That's what it is. Okay? So does anybody have any more questions about hydrohalogenation? So somebody in the chat asks if this reaction is an SN1 reaction. And that is a really good question. And the answer to that question is no, because if you look here, we're doing an addition reaction because we're going from a double bond to two sigma bonds. An SN1 reaction is a substitution reaction where we replace something. This is similar to SN1 because we end up having a carbocation intermediate and doing a front side and a back side attack, but it's not SN1. Now, just to reiterate, the carbocation is going to be sp2 hybridized, which means it's going to be trigonal-planar. Essentially, what that means is it's going to be easy to attack from both sides of that carbocation, and thus we will get both syn and anti-addition, because this hydrogen has already been added on as a solid wedge or a dashed wedge. That's not going to change, okay? And so then what determines if it's going to be syn or anti is where this halogen here adds on to, whether it adds on as a solid wedge or a dashed wedge. Okay, does that clear up any questions that you had about hydrohalogenation? If so, we're going to move on to hydration with an acid catalyst. So this one is very similar to hydrohalogenation because the first thing we do is we add a hydrogen and we make a carbocation intermediate. The main difference between hydration with an acid catalyst and hydrohalogenation is that that H plus ion, that hydrogen, comes from an acid rather than an HX. So rather than an HCl or an HBr, this will come from something like H2SO4 or H3O plus. Okay? And so then we end up with that carbocation intermediate. And again, using the same rules as before, the hydrogen is going to add to the less sterically, or not the less sterically hindered, but the less substituted carbon in order to create the more stable carbocation. Okay? And again, since we form a carbocation, we're going to skip this next step really quickly and look at the end. We are going to form both the syn and the anti. So notice something here. Whenever we form a carbocation, we will form let me say that again. Whenever we form a carbocation, the reactants will add either syn or anti at the same time. Okay? And that is because the carbocation is sp2 and trigonal planar. Okay? And so we can see here that after we have a carbocation, our water molecule is going to add, and then it's going to be deprotonated, making our final product. And remember, hydration is just adding H2O, and we can see here that we add both an H and an OH, therefore being H2O. Okay? And I want to mention something very quickly before we move on. This method, this hydration, can also be used to make ethers. So if instead of using water, we use ROH. So in this example here, I used ethanol, which is just two carbons with an OH attached to it. And so you can see here that I use the H2SO4. It's just drawn slightly differently in order to represent the hydrogen bond a little bit better. So we can see here that the double bond grabs onto the hydrogen leaves from the acid, we end up with a carbocation, the ROH adds to it, so this could be ROH or H2O. If we add H2O, then we'll make an alcohol. If we add an ROH, then we'll make an ether. And then we see that the acid, or I should say the conjugate base from before, we can see that the OSO3H comes from the acid that we used to protonate the alkene. We'll deprotonate that positively charged oxygen there, and then we end up with just our ether. And again, this will also add syn and anti because we have that carbocation. The only reason I didn't write it out here is because I was running out of time and space on this page when I was making this whole thing here. Okay? So does that make sense with hydration? Hydration and hydrohalogenation are very similar. The big difference is that hydration is using water and an acid, whereas hydrohalogenation is just using HX, being like HBr, HCl, HI, that sort of stuff. Okay? So now let's go on to halogenation. This is where things get a little bit different. And this is because when we have halogenation, we're adding two halogens. We can see here that halogen is the only word in halogenation. So we're just going to be adding two halogens. So we can see here, this first step looks a lot different from before. And so we can see here that the double bond is going to grab onto one of the halogens at the same time as the halogen grabs onto the double bond. So we end up with something called a bridged halonium ion. And so this is sort of like an epoxide, except instead of oxygen, we have a halogen. This halogen can be Br, I, those types of things. And then what happens is the remaining halogen, so the halogen that used to be part of this X2 that was broken off before, does a backside attack on one of these carbons. It does not matter which at this point, because we are going to end up with a product with a halogen on either side. Okay? So let me erase this really quickly. So we can see here that even if the X added to this side, we would end up with the same types of products. And this is because the X, there's going to be one X on either carbon no matter what, okay? And so we can see here in addition, and when we talked about epoxides, we always said that the nucleophile, or in this case the X, will react by doing a backside attack because it's going to want to stay as far away as possible from this electron-filled bond because you see it's negatively charged and wants to stay away from other negatively charged things. So to stay away from that bond as much as possible, it will add to the backside. Okay, and so then that's where we get this product from. This second product here is formed by sort of the enantiomer of this bridged halonium ion, where instead of being a solid wedge here connecting the X to the carbons here, it's a dashed wedge, okay? But what's important to notice is that we end up with only anti-addition. So when we have a bridged halonium ion, we're only going to end up with anti-addition, okay? So, just to reiterate, when we have a carbocation, we'll do syn and anti-addition. When we have a bridged halonium ion, we're only going to do anti-addition. And the reagents for halogenation is just going to be an alkene and then X2, where X is Cl or Br. Okay? And so now let's look at halohydrin formation. Yes, I know we're going through a lot of reactions like really, really fast right now, but if you just slow down and look at each one of these reactions separately, they'll start to make a lot more sense, okay? So halohydrin formation. So halo, meaning a halogen is added. Hydrin means a hydroxy group is added. So now we have a halohydrin formation. You may recall that we used a halohydrin when forming epoxides. And so, for example, let's say that we wanted to form an epoxide for whatever reason from a double bond. So we would form a halohydrin first and then form an epoxide using that halohydrin. That's just one of the examples that we would use this sort of option for. So the same thing, the same first step as halogenation occurs. We have X2. One of the halogens attacks the double bond at the same time as the double bond attacks the halogen, and we end up with a bridged halonium ion intermediate. Okay? And then the same thing happens as before, except instead of using X, we're gonna be using H2O. So what occurs is a backside attack of H2O, and then we have a positively charged oxygen, which one of the hydrogens is taken from the halogen from the beginning. So this halogen right here is the same as this halogen right here. Okay, so that's where we got it from. So then we end up with the anti-addition of X and OH. And again, since we have a halonium ion intermediate, we're going to have only anti-addition. Okay? And the reagents that we use for this are the same as the reagents for halogenation, except we also add water. All right. So now let's go. Oh, also, one thing to note with this guy here is it's going to add the X to the less substituted carbon. And this is sort of similar to the Markovnikov rule, except instead of forming a more stable intermediate carbocation, it's going to form a more stable transition state. Again, I was kind of running out of time when I made this because I was making those other two documents, so I did not draw it here, but it is drawn in the PowerPoint, I think, where you can see how the intermediate, or not the intermediate, but the transition state causes the halogen to be added to the less substituted carbon. Okay? All right, so let's talk about hydroboration oxidation. This is where a lot of people get tripped up, especially with the name. But if we break it down, hydroboration, we're adding hydrogen and we're adding boron, oxidation, and then we add oxygen. So what occurs is hydroboration oxidation. The first step is the hydroboration. And we can see here that the hydrogen ends up added to the more substituted carbon. And this is anti-Markovnikov. This is the only one that's anti-Markovnikov. And this is because it makes a more stable transition state, similar to how we chose where the OH group goes in the halohydrin formation. Okay? And so then the second part, we add H2O and H2O2 to form our actual answers. And this second part of the mechanism is a little bit advanced. It's really long, and again, this is the third time I've mentioned it. I was running a little bit short on time, but I don't think that you guys would have to know this mechanism, but I would go and study it if you have the time. But I would say personally, I don't think it's super important, especially compared with all of the reactions you guys have to know. Okay? The only other thing I want to mention about hydroboration oxidation is that it only does syn addition. This is the only one that only does syn addition. So remember, the first two, we did syn and anti because we formed a carbocation. We did only anti for halogenation and halohydrin formation because it made a bridged toluene ion intermediate. And then hydroboration oxidation is the only one that does syn addition only. And we can see here that the reagents are a little bit different. I listed them as 1 and 2 rather than just all of them together. And this is because we use the BH3 and the THF. The THF is just an aprotic solvent that this occurs in. So you'll probably see either THF, DMSO, any aprotic solvent will work. THF was just written out in the book, I think, or at least in the PowerPoint. And then the second step is using H2O and H2O2. It's very important to list these two steps separately because BH3 will be oxidized by the water and the H2O2 if they are in the same reaction and not separated by 1 and 2. Okay? So I know I went through that really, really quickly, but does anybody have any overarching questions about any of this stuff? Okay, it looks like we're okay for now.
I have a question.
Oh, go ahead.
So for all of these except the hydroboration, it's always going to be going to the less substituted except for hydroboration?
Yes, exactly. It's just sort of harder to see, especially with halohydrin formation. You sort of consider the so what I always did when this is like not completely correct, but what I always did is I always considered, oh, the halogen will act as the hydrogen in this case. So to be Markovnikov, the halogen will add to the less substituted carbon. And somebody else asked, I thought DMSO was only used in halohydrin. DMSO can be used in anything that needs a polar aprotic solvent, same as THF. So just don't be tripped up if you see other types of solvent pair with BH3 as long as those solvents are aprotic. So as long as they're not something like methanol or like any alcohol or water. Okay? And yes, every time the hydrogen will go to the less substituted carbon, so the carbon with more hydrogens, except for a hydroboration oxidation. Okay? So does anybody have any more questions before I finish up? And again, this will be available in the Google Drive link that is in the description of this video. Okay? All right, so that was a really good exam 3 part 2, and I wish you guys all the best, and I hope you do really well. Okay?
Thank you.
No problem.
Thank you so much.
Thank you.
Thank you.
Thank you.